And welcome back. As we continue our cosmic journey, as we examine stars, we are now shifting our focus to look at the spectra of said stars. So the first thing we have to understand when we're talking about stars is we're mostly going to look at analyzing the starlight to really get a good spectrum analysis. In 1814, the German physicist Joseph Fraunhofer observed that the spectrum of the sun showed dark lines crossing a continuous band of colors. In the 1860s, English astronomers Sir William Huggins and Lady Margaret Huggins succeeded in identifying some of the lines in stellar spectra as those of known elements on Earth, showing that the same chemical elements found in the sun and planets exist in the stars. Since then, of course, astronomers have worked hard to perfect experimental techniques for obtaining and measuring spectra, and they have developed a theoretical understanding of what can be learned from said spectra. And of course, we have, done some viewing of various spectra already in this class and have an understanding of how certain elements present certain distributions when we start looking at things like absorption lines. Now, today's spectroscopic analysis is one of the cornerstones of astronomical research. So let's look at the formation of stellar spectra. When the spectra of different stars were first observed, besides our own sun, astronomers found that they were not all identical. Since the dark lines are produced by the chemical elements present in the stars, astronomers first thought that the spectra differ from one another because stars are not all made of the same chemical elements. But the primary reason the stellar spectra look different is because the stars actually have different temperatures. Most stars have nearly the same composition as our sun, with only a few exceptions. Hydrogen is by far the most abundant element in most stars. If we go and look at the spectrum of hydrogen, we can of course see those familiar lines there that we would see in our own sun. However, the lines of hydrogen are not seen in the spectra of the hottest and of the coolest stars. And why is that? Well, in the atmospheres of the hottest stars, hydrogen atoms are completely ionized. Because the electron and the proton are separated, ionized hydrogen cannot produce absorption lines. In the atmospheres of the coolest stars, hydrogen atoms have their electrons attached and can switch energy levels to produce said lines. However, practically all the hydrogen atoms are in the lowest energy state in these stars, and thus can only absorb those photons, able to lift an electron from that first energy level into a higher energy level. There are very few ultraviolet photons in the radiation of a cool star. Now, what does this mean? Well, it means that if we observe the spectrum of either a very hot or a very cool star with a typical telescope on the surface of the Earth, the most common element in the star, hydrogen, will show very weak spectral lines or none at all. So the hydrogen lines in the visible part of the spectrum, we call Balmer lines, are the strongest in stars with intermediate temperatures, such as our own sun. Calculations show that the optimum temperature producing visible hydrogen lines is about 10,000 Kelvin, and at this temperature, an appreciable number of hydrogen atoms are excited to that second energy level. They can then absorb additional photons, rise to higher levels of excitation, and produce a dark absorption line. Similarly, every other chemical element in each of its possible stages of ionization has a characteristic temperature at which it is most effective in producing absorption lines in any part of the spectrum. So, if we can analyze the different spectra, can we classify them? Well, astronomers use these patterns of lines observed in stellar spectra to actually sort stars into spectral classes. Because a star's temperature determines which absorption lines are present in its spectrum, these spectral classes are therefore a measure of its surface temperature. And there are actually 7 standard spectral classes. The hottest to coldest are going to be O, B, A, F, G, K, and M. And if you want to remember that, there's a lot of good mnemonics that you can use to come up with words that can stand for each one. You can make your own sentence if you want. But again, O, B, A, F, G, K, M are the order of those stars. Now recently though, astronomers have added 3 additional classes for even cooler objects, L, T, and Y. Now each of these spectral classes, except for possibly the Y class, which is still really kind of being defined, is further subdivided to 10 subclasses designated by the numbers 0 through 9. A B0 star is therefore going to be the hottest type of B star. A B9 star is the coolest type of B star and is only slightly hotter than that of an A0 star. So we look at the spectral classes for stars. Let's go ahead and start with OBAFG. And if we look at here, we can see some cool information. So for example, we start off with blue as the top of the spectral classes for color. And then we move to a blue-white, a yellow-white, and finally a yellow. And our approximate temperatures here, you notice for a blue star, are greater than 30,000 Kelvin, which is extremely warm for the surface of that star. Blue-white stars are ranging anywhere from 10 to 30 Kelvin. White stars about 7,500 all the way up to about 10,000. Yellow-white stars, much like our own sun, are about 6,000 to 7,500. And yellow stars are 5,200 to 6,000. And you can see, of course, our principal features here. The O star has neutral and ionized helium lines, weak hydrogen lines. Blue-whites, neutral helium lines, strong hydrogen lines. The white stars, strongest hydrogen lines, weak ionized calcium lines, and weak ionized metal, and so on and so forth. And then if we go ahead and look at the next set of stars, K, M, L, T, and Y, we can see our colors are shifting even more. So with K stars, we are now orange, M are red, L also red, but it's typically much more shifted. T is magenta, and Y is now actually infrared. And we look at those temperatures there. We have about 3,700 to 5,200, 2,400 to 37, 1,300 to 2,400 for our L stars, 700 to 13 for our T, and less than 700 Kelvin for our Y. So these are very cool objects by comparison. And if you look at the lines here, as we start moving into the LTY, you'll notice that the hydrogen bands that are very familiar in some of those upper level ones disappear, and we start seeing other elements become much more prominent, such that when we get to T and Y, we are actually getting methane and ammonia as the principal features. So let's look at those spectral classes of L, T, and Y just a little bit more. Objects with masses less than about 7.5% of the mass of our sun do not become hot enough for hydrogen fusion to take place. Even before the first such failed star was found, this class of objects with masses intermediate between stars and planets was given the name of brown dwarfs. Now, brown dwarfs are very difficult to observe because they're extremely faint and cool, and they put out most of their light in the infrared part of the spectrum, so they're not something that's necessarily able to be visible with the naked eye. It was only after the construction of very large telescopes and the development of very sensitive infrared detectors that the search for brown dwarfs succeeded. The first one, of course, was found in 1988, and since then, thousands of others have been found. In Class L brown dwarfs, the lines of titanium oxide, which are strong in M stars, have disappeared. This is because L dwarfs are so cool that the atoms and molecules can gather into dust particles in the atmospheres. Lines of steam are also present, along with the lines of carbon dioxide and neutral sodium, potassium, cesium, and rubidium. Methane lines are now stronger in the Class T brown stars, as methane exists in the atmosphere of the giant planets in our own solar system. Think about our composition of things such as Uranus and Neptune. And in 2009, astronomers discovered ultra-cool brown dwarfs with temperatures between 500 to 600 Kelvin. Now, these objects exhibit absorption lines due to ammonia, which are not seen in T dwarfs. So a new spectral class Y was created for these objects. Now, this image here kind of shows the size and surface temperature of brown dwarfs with relation to the Sun, red dwarf star, and also Jupiter. So here, of course, we have the Sun. You can see it's the largest object here. We then move down into a red dwarf star just to get you some size comparison. And then, of course, we start moving down into some more brown dwarfs. These, of course, are big enough to be brown dwarfs. They are not to the point where Jupiter is here. Notice Jupiter, even though Jupiter is massive, it does not have the mass enough to kind of go into this hyper state that we see here with some of these larger stars. Remember, the big difference is that for brown stars to exist, they need to have enough mass. Jupiter does not have enough mass. It is massive for our solar system, but it does not have enough mass in order to handle all the challenges that come in with being able to be mass enough to turn it to a star. Now, that's because most brown dwarfs actually start out with atmospheric temperatures and spectra very similar to that of true stars. Think about Jupiter's own composition, with it having a composition that is mostly hydrogen and helium. An independent measure of mass is required to determine whether a specific object is a brown dwarf or a very low mass star, because this does make a difference. Since brown dwarfs cool steadily throughout their lifetimes, the spectral type of a given brown dwarf actually changes with time over a billion years, and more from like M through L, T, and Y spectral types. So, what is the difference between a low mass brown dwarf and a high mass planet? Think about our Jupiter. Like, we know Jupiter is massive, but where is that cutoff threshold for it to turn into a brown dwarf? Well, an interesting property of brown dwarfs is that they're all about the same radius as Jupiter, regardless of their masses. If you looked at that previous image, we saw that those brown dwarfs were the same size as Jupiter. And this actually covers a range of masses that range anywhere from 13 to 80 times the mass of Jupiter. And one of the issues we have is that because they are Jupiter's size, but just more massive, it can make distinguishing a low mass brown dwarf from a high mass planet very difficult. And so what's the big difference? Like, how do we know? Well, currently the International Astronomical Union, or IAU, considers the distinctive feature to be deuterium fusion. Though brown dwarfs do not sustain regular hydrogen fusion, they are capable of fusing deuterium, which means you're taking a single hydrogen and you're fusing with that single proton, that neutron. The fusion of deuterium can happen at a much lower temperature than the fusion of hydrogen. If an object has enough mass to fuse deuterium, it is therefore a brown dwarf. If we look at our own Jupiter, it does not have that mass, and because it does not have that mass to it, it cannot fuse deuterium.